Hi guys, so today we're going to take a look at question 2 of the 2017 exam paper 1. Okay, so we have a complex number z equals minus root 3 plus I, and we want to use de Moivre's theorem to write z to the power of 4 in the form a plus b root ci, where a, b, and c are integers. Okay, so we want to use de Moivre's theorem. Well, whenever they mention any sort of theorem, you should immediately, write down, what is that theorem? What does that theorem state? And de Moivre's theorem states that if we have a complex number in this form, r cosine theta plus I sine theta, also known as polar form, and we take it to some power, then we can write this as r to the n times cosine of n theta plus I sine n theta. Okay, so we have a problem. We have our complex number in the form z equals minus root 3 plus I in standard form z equals a plus bi, and we need to get it into the form r cosine theta plus I sine theta. But fortunately, we have a very easy step-by-step process to do this. So if it's in the form a plus bi, which it is, with a is equal to minus root 3 and b is equal to 1, the coefficient of I, then we can write this should be cosine of theta. R is equal to the magnitude of z, which we have a formula for, the square root of a squared plus b squared. So when we're going from the a plus bi form to the polar form. And we have a formula for theta. Theta equals the argument of z, which the formula for is tan inverse of b over a. Okay, and now we can just sub into these formulas. So r equals the square root of minus root 3 squared, which will just be 3, plus 1 squared, 3 plus 1. So this will just be the square root of 3 plus 1, square root of 4, which is 2. So r is 2. And now for theta, theta is tan inverse of b over a. So tan inverse of 1 over minus root 3. And if we put this into our calculator, we'll get minus pi over 6. So if this is our complex plane, then it's approximately this angle here. So it's saying z is in this fourth quadrant. But there's actually a problem, because we know that z is not in this quadrant. Z has a negative real value and a positive imaginary value, which means it should be in this quadrant. And these are the two quadrants in which tan is negative, which is why we have a negative value here. So the equivalent angle in the second quadrant, which we know that our complex number lies in, is this angle. this angle here. This is our, sorry, no, that's not our theta. This is our theta. And so if this angle is pi over 6, and the whole thing, the angle of a straight line, is pi, then our theta equals pi minus pi over 6. And this is sort of this is probably the trick of the question, to notice that the angle is not minus pi over 6. It's not this angle here. And it's kind of just important to understand this complex plane and where this complex number would lie in the complex plane. So theta is pi minus pi over 6, which is just 5 pi over 6. Okay, so we have our value r and our value theta, so we can write z as 2 times cosine 5 pi over 6 plus I sine 5 pi over 6. And actually a good way of checking out, a good way of noticing that minus pi over 6 wouldn't work is, let's say you thought that it was minus pi over 6. And if you got z equals 2 cosine minus pi over 6 plus I sine minus pi over 6, well then if you multiplied this out, you should get the minus root 3 plus I, but you wouldn't. You wouldn't get that. You would get root 3 minus I. So multiplying these out, when you get some answer here, multiplying out to see if it got what you know it should be is always a good idea. So that might be where you might notice that there was a mistake, somewhere. And then if you want to verify this yourself, and you always should, multiply this out, and you should get what we know z to be. Okay, so this z to the power of 4 is equal to this expression to the power of 4, obviously, plus I sine 5 pi over 6. And using de Moivre's theorem, this is r to the power of 4, 2 to the power of 4, times cosine 4 theta, which is 20 pi over 6, plus I sine 20 pi over 6. Now you can simplify 20 pi over 6, but there's really no need to, because we're not going to be leaving it in this form. This is technically z to the power of 4, but they wanted it in this form here, a plus b root ci. So now we're going to have to go back. And it's actually a lot easier to go from this form, polar form, to the standard form. You just multiply it out. So if we multiply this out, we'll get 16 times cosine 20 pi over 6, which is minus a half, plus I sine 20 pi over 6, which is minus root 3 over 2. And this gives us minus 8 root 3 I. So exactly the form that they're looking for. Now on to part B. The complex number omega, or W, is such that the magnitude of W is 3, and W makes an angle of 30 degrees with the positive sense of the real axis. If T equals ZW, write T in its simplest form. Okay, so the magnitude of W is 3, and we know that the magnitude of W is R in, let's call this RW. So in this polar form, R cosine theta plus I sine theta, we know that R represents the magnitude of the complex number. So if we write W as RW cosine, let's call this theta W, plus I sine theta W, then RW is the magnitude of W. So W equals 3 cosine theta W. That's not theta times W, that's like this, plus I sine theta W. Okay, and they've also told us that W makes an angle of 30 degrees with the positive sense of the real axis. And we know that the angle that a complex number makes, let's just write this down. We know that theta is the angle a complex number makes with the positive sense of the real axis. And what does this mean? Okay, so in the previous question, we said that theta was, let's just clear up this diagram a bit. So theta here was this angle, which is exactly the angle that the complex number z makes with the positive sense of the real axis. So this is the real axis, and so the positive sense of it is here. So the angle that z makes with here is exactly theta. That's how we define theta in the polar form. And so they've given us this value of theta. So theta W is 30 degrees. Or pi over 6 in radians. And I prefer using radians for complex numbers, but it really doesn't make any difference at all. So W equals 3 cosine pi over 6 plus I sine pi over 6. Okay, so there's a few ways that we could do this. So now we're trying to write the product ZW. T equals ZW. And now there's a couple ways we could do this. We could write Z and W in standard form, and we would just get AZ plus BZI, so the standard form of Z, times AW plus BWI, the standard form of W, and we would multiply them out together and we would get an answer. And that would be fine, that would be perfectly fine. You then simplify that down as much as possible. Nothing wrong with that approach at all. But I want to actually show you a different approach for multiplying complex numbers when you have the polar form. So a really useful thing about the polar form is that it makes multiplication of complex numbers really easy. And I mean, if you think about it, a power, like in de Moivre's theorem, is just multiplication of complex numbers multiple times. So for example, z to the power of 4 is just z times z times z times z, which is technically a multiplication of complex numbers. So if we have z times w, well, let's write out the form of z. So z equals 2 cosine 5 pi over 6 plus I sine 5 pi over 6 and w is 3 cosine pi over 6 plus I sine pi over 6. Okay, and when you multiply two complex numbers in this form, there's a trick you can do. So the product of these two is just the product of the magnitudes, so it's 2 times 3, and then you sum the arguments, so cosine 5, so you sum the angles, 5 pi over 6 plus pi over 6 plus I sine 5 pi over 6 plus pi over 6. And someday we can go through, at some point I'll go through why this works, why you multiply the powers, multiply the magnitudes, although that kind of makes sense. You would just bring this over here. But why you just sum together the angles is a little bit weird. So this would just be 6 by cosine pi plus I sine pi which is just 6 by minus 1 plus I times 0. So it's just minus 6. So t equals minus 6. And if you do it this way, just multiplying both the standard forms, which would be perfectly fine, you would also get t equals minus 6. And so now I just want to quickly, a little bit of a tangent, and if you want to finish the video here, that's perfectly okay. That is the end of the question. But this is kind of where we get de Moivre's theorem. So de Moivre's theorem is r times cosine theta plus I sine theta to the power of n is equal to r to the power of n times cosine n theta, so summing the angles, plus I sine n theta. Let's just put this in brackets. And so let's say for an example we took n to be 2, so we're squaring a complex number, r times cosine theta plus I sine theta. Well, this is just, so if we use de Moivre's theorem, this would just be r squared times cosine 2 theta, or sorry, this is squared. This would be r squared by cosine 2 theta plus I sine 2 theta. Okay, that's our answer. And now let's do it the other way, this multiplication way that we just talked about, that we just used to find t. So z squared, or r cosine theta plus I sine theta squared, is just r times cosine theta plus I sine theta by itself. R times cosine theta plus I sine theta. And so if we did our multiplication way, this would be the product of the magnitudes, which is just r by r squared, and then add the angles, so theta plus I sine theta plus theta, which of course is just r squared cosine 2 theta plus I sine 2 theta. And you can imagine if there were more products, let's say it was cube, there was another one here, then we would just get r cubed times cosine 3 theta. And this is where de Moivre's theorem comes from. So that's just a little bit of extra info as to how this multiplication method relates to de Moivre's theorem.